Welcome to Learning to Engineer. How to supply power to a BJT? There are two kinds of power that's involved here. One is the input supply and other one is the operating supply. Say for example, you're going to use BJT as an amplifier. Your unamplified signal at the input, which is from sensors, your mobile phone or whatever purpose. Okay, these signals will be your input to your BJT and it will be amplified at the output. This is the actual operation of your BJT. But to make the BJT operate by itself, you need to supply some power, right? Your mobile phone doesn't talk to your friend by itself. You need to talk on the receiver's end. Plus, for its operation, you need to have a battery and you need to charge that too. This operating supply is what is under our focus in this video. We have a 3-terminal device in a BJT, right? If it is a 2-terminal device, the connection is obvious and you know how to connect a 2-terminal device. Plus goes to plus, minus goes to minus. But in a BJT, you have a emitter, base and a collector. You can either supply power to these both, to these both. That is also one configuration. You can also do it in another method. You can connect this to these both and these both. So there are 3 different configurations when you think like this. The common base, where the base will be common to the emitter and the collector. Second one is the common emitter, where the emitter will be common to the base and the collector. And third one will be the common collector mode, where the collector will be common to both the base and the emitter. So there are 3 ways of designing this circuit. Keeping this apart, there are different biasing modes where you can connect the power supply directly to the base, directly to the collector, or you can divide the supply such that a part of it goes to the base, makes the BJT operating in the active region. There are different modes of biasing, there are different modes of connecting the BJT to it. When you think of a circuit where which one should be common, the base or the emitter or the collector, when you think like this comes under the modes of operation, and after you decide which terminal is going to be common, you have to decide how should you bias from the external, whether you are going to connect directly to the base or how is it. Those are the biasing modes. We are going to look at that in this video. In order to help you understand better, we will also solve some problems. Problems are not always designed to test your knowledge. Today, we are going to enhance our understanding with the biasing modes with the help of problems. Let's get started. The first one is the common base mode. In the common base mode, you will have the base of the transistor to be common between the emitter and the collector, and this is how the input characteristic is. The input characteristics describes how we are getting the input current IE flowing into the BJT. This IE is the input current and IC is the output current. And we have discussed this in detail in the previous video. Similarly, there are circuit structures for common emitter and common collector modes also, where one of them will be forward biased and the other junction will be reverse biased, and you will have a similar characteristics curves also. Now, we will focus on the biasing schemes of BJT in this video. This is a fixed bias circuit. In a fixed bias, you will have a common power supply that is connected to the base as well as the collector. But the thing is, the base resistor will be much higher than the collector's resistor, so that the input current will be minimized and hence you will supply more IC through this. Okay, so the value of RB is greater than IC. The resistance and current are inversely proportional, so both of them are connected in parallel. So obviously same voltage will be connected across them. So naturally the value of IB will be lesser when compared to the value of IC. This is the fixed bias scheme. The advantage is that only one single power supply you are using this, and you are making it across the collector as well as the base. This is the fixed bias. Next is the collector feedback loop. In the collector feedback loop, you will have an extra resistor called as RF, which acts as a feedback from the output to the input. And here you will have a base resistance and a emitter resistance too. Here again you have one single power supply where you are sending the power to the collector via the RC, and it splits into two parts. One is called as the IF and here is IC. So IF will only be a part of IC which is added into the base. Here again this signal splits into two. One goes via the RB to the ground and only a part of it is connected to the base, IB. Okay, so naturally it is designed to make IB as small as possible so that you will get a large IC. Okay, this is the collector feedback loop. We are going to look at one problem in this model so that you will be able to understand the purpose of this in a better way. Next is the widely used voltage divider bias. In the voltage divider bias, you will connect two resistors in series. R1 and R2 are in series. When two resistances are in series, the voltage divides across them. Naturally, this is also designed to reduce the value of IB. You have a zero point 0.7 volt drop between the P and the N terminals of any semiconductor device. So, because of this drop again, the voltage will be reduced further and IB will be less. In all these three schemes, by different methods of connection, you are ensuring that IB is smaller than IC, be it fixed bias, collector feedback loop, or in voltage divider bias, you are ensuring that this supply is made to both the collector and the base terminals, and via the choice of the resistors R1 and R2, we are ensuring that the value of VB is lesser. Okay, because in two resistors you are going to get the share of only R2 across VB. So this happens both in collector feedback loop as well as in fixed bias. Okay, so all these schemes will appear similar to you, but there are slight differences. In fixed bias, you will have only three resistors, one at each terminal. But in voltage divider bias, you are dividing the resistance and making the value of VB even more small. So this is the widely used circuit compared to all the three circuits. We will look at one problem in each type. Consider this fixed bias circuit. The value of the base resistance is 240 kilo ohm and the collector resistance is 2.2 kilo ohm. In this question, you have to find out the value of base current, the value of collector current, and hence the voltage at the base with respect to ground and the voltage between the collector and the emitter. The direction of the base current is into the P terminal. Okay. With this can simply be achieved by Kirchhoff's laws and no need to memorize any formula for the biasing schemes. I am sure in your books you will find some equations and some formulas to memorize, but I promise you if you do know KCL and KVL and how to apply to this circuit, you don't have to memorize any of the formulas at all. Okay, we are going to solve all of this without any formulas. To this loop, we are going to apply Kirchhoff's voltage law. Okay, so 12 is equal to the current that's going into the 240, which is IB, multiplied by 240K plus this voltage 0.7 volt, because that's the voltage that exists between the base and the emitter region. So naturally you can find out the value of IB, right? IB is equal to 12 minus 0.7 divided by 240K. This is equal to 47.08 microampere. Now let's find out the value of IC. IC is equal to beta times IB. And what is IE? IE will be beta 1 plus 1 times IB. Okay. This is beta times IB and this is beta plus 1 times IB. So IE will be a little greater than IC in this case. Not only in this case, in any transistor for that matter. IE is designed to be a little greater than IC. Why is that so? And how is the transistor designed for that? You have a N sandwiched between two layers, right? Both of them are P materials. When that is the case, how can you ensure that IE will be little greater than IC and not exactly same? Keep thinking, and the answers for this question will be followed in my next video. Okay? So IC is equal to, what is the beta that is given in this question? Beta is 50. So it is 50 into 47.08 microamperes. What is IE? IE will be 50 plus 1, 51 into 47.08 microampere. So if you calculate, you get the value of IC as 0.35 milliampere. And if you compare, the value of IB is 47.08 microampere. Micro means into 10 power minus 6. Okay, IC is in milliampere, which is into 10 power minus 3. And IE is also in milliampere, which is into 10 power minus 3. The base is really small. The base current is really small, and IC is 2.35 milliampere and IE is 2.40. This is how you will get in any transistor which operates in an active region. All the three currents will be positive, and you will observe that the value of IB is much lesser. This is designed such a way that the IB is so less. The N region is designed to be very thin. The sandwich region, be a NPN transistor or a PNP transistor, the base region substrate, we call that as substrate because this is the region which sandwiches the collector and the emitter. It is designed to be so small that the majority carriers of that region is divided between larger P regions in a NP transistor. Okay. So naturally you will have less and less carriers available in the base region for conduction. So this is how we are ensuring that the value of IB is small, and plus if you observe the biasing circuit, the 240 kilo ohm is connected in the base and just 2.2 kilo ohm is connected in the collector. This is to ensure that you have larger collector voltage than the base voltage. Okay. Now, let's solve the problem in collector feedback loop. Find the value of IC and VCE for this circuit. This is a collector feedback loop, and if you observe, 250 kilo ohm is connected at the base and just 4.7 kilo ohm at the collector, and same for the emitter. Emitter is just 1.2 kilo ohm. The base resistance will always be ensured to be larger internally as well as externally. Okay, so let's apply KVL into this loop. Let us consider the current path like this and apply KVL into this. The beta of the transistor is given as 90, and now we have to apply KVL to the base loop. And do have it in mind that 0.7 volt is the voltage between the base and the emitter. And now let's apply KVL. 10 volt is equal to 4.7K into I1 plus 250K into IF plus 0.7 plus 1.2K into IE. We have three current terms over here, I1, IF and IE. What is I1? I1 is split as IF and IC, right? IF is nothing but the base current IB. So I1 will be IB plus IC. And what is IF? IF is IB, and that is why I1 has become IB plus IC. What is IC? Beta times IB. And what is IE? Beta plus 1 times IB. So in this case, this is equal to 90 IB and IE will be 91 IB. IF is nothing but IB. So what is I1 now? I1 will be IB plus beta IB, which is equal to IB into beta plus 1, which is 91. So let's substitute all the three currents into this equation. This implies that 10 is equal to 4.7K into I1, which is 91 into IB, plus 250K into IF, which is IB, plus 0.7 plus 1.2K into IE, which is 91 into IB. So in all the terms we have IB common, and if you take IB to one side, you will get 10 minus 0.7 divided by the whole term. And now we can get the value of IB as 11.91 microampere. Okay, so now I have found out the value of IB, and similarly we can apply the Kirchhoff's voltage law to the collector loop also. I'll erase this lines and stuff. Okay, so when we apply Kirchhoff's voltage law to this loop, we have to consider the voltage between 4.7 kilo ohm and the voltage between the collector and the emitter. This VCE plays an important role in deciding in which region the transistor operates. The VCE should ensure that the collector emitter junction is reverse biased in case of emitter common. Okay, so VCE plays an important role to know in which mode of operation the transistor is into. Okay, so we will apply KVL to this loop now. Kirchhoff's law to the collector loop. Okay, so you will get 10 volt is equal to 4.7K into I1 plus VCE plus 1.2K into IE. Okay, so we just saw that I1 is the split of the base and the collector currents. So 4.7K into IB plus IC plus VCE plus 1.2K into beta plus 1 into IB. We have just found out the value of IB as 11.91 microampere, and what is the value of beta? Beta is 90. So we can substitute that and find out the value of VCE. What is IC? IC is equal to 90 into 11.91 microampere. So you will get the value of IC, substitute IC here, and hence find out the value of VCE. 3.69 volt. Okay, so VCE in this case is positive. Just observe this, the collector terminal is positive, 3.69 volt. So this is positive and this is negative. This is a NPN transistor, this is a N junction. To N junction, when you are applying a positive voltage, then this terminal will be reverse biased, and if you observe, the base current is going into the base terminal. We found out that the value of 11.9 microampere. So if you observe, this terminal has a higher potential than the base terminal, and that is why the current is flowing from this point, collector terminal, to the base terminal. So this is forward biased and this terminal is reverse biased. So this transistor is in active region. Okay, so in the previous video of common base mode of a transistor, we saw how we are going to bias the transistor in common base mode. One set of junction was ensured to be in forward bias and the other junction was in reverse bias. You know exactly about how the majority and minority carriers move. Please check out that video and you can solve the problems very easily.